This is Ashwita from Computer Science and Engineering Department. I am here to give a presentation on uh, origin of energy bands regarding engineering physics subject. Outline of my presentation. Introduction, atomic orbitals, bonding and anti-bonding orbitals, periodic potential, band gap, band structure calculation, types of energy bands, influence of temperature and doping, applications of energy bands. Energy bands are a fundamental concept in solid state physics. They describe the distribution of energy levels available to electrons in a crystalline solid. Understanding the origin of energy bands is crucial for explaining the electrical and optical properties of materials. Energy bands in solids. When atoms are brought together, each state split into n states of different energy. That is, the number of states equal the number of atoms because of the overlapping wave functions. Since a sample of solid material contains a large number of atoms, example in 1 centimeter cube of copper, there are 10 power 23 atoms. Each state splits into energy levels so close together that energy bands are formed. Each band consists of essentially continuous range of allowed energies. The energy bands are separated by energy gaps known as band gaps. The width of a band depends on the lattice spacing. Atomic orbitals. In a single isolated atom, electrons occupy discrete energy levels within atomic orbitals. When atoms come together to form a solid, their discrete energy levels overlap and combine. The interaction between neighboring atoms leads to the formation of energy bands in the solids. Anti-bonding orbitals. In a solid, the combination of atomic orbitals can result in the formation of bonding and anti-bonding molecular orbitals. Bonding orbitals have lower energy than the original atomic orbitals and promote electron delocalization. Anti-bonding orbitals have higher energy and hinder electron delocalization, leading to energy band formation. Two energy diagram for two pi molecular orbitals in a typical pi bond. Two adjacent p atomic orbitals can engage in constructive overlap to form two pi molecular orbitals. Constructive overlap results in the bonding pi orbital, which is lower in energy than the individual p atomic orbitals. Destructive overlap results in an anti-bonding pi orbital, that is pi star, which is unstable. Periodic potential. The periodic arrangement of atoms in a crystal creates a periodic potential energy landscape. Electrons in a solid experience this periodic potential, leading to the formation of energy bands. The periodic potential causes constructive and destructive interference of electron waves, influencing band structure. Band gap. The energy band structure of a material can contain regions where no electron states are allowed, known as band gaps. Band gaps can be either direct or indirect, affecting the material's electrical and optical properties. The size and nature of the band gap determine whether a material behaves as a conductor, insulator, or semiconductor. This is the different types of band gaps. Band structure calculation. The energy band structure of a material can be calculated using theoretical models such as the tight binding or density functional theory. These calculations consider the interaction between electrons, crystal structure, and periodicity to predict the energy band diagram. Experimental techniques like angle resolved photoemission spectroscopy can validate the theoretical band structure predictions. Types of energy bands. Energy bands in a material can be classified as valency bands and conduction bands. Valency bands are filled with electrons at low energy levels, while conduction bands are empty or partially filled with higher energy levels. The energy separation between the valency and conduction bands determines the material's conductivity. These are the energy band gaps in materials. In insulators, the gap between valency band and conduction band is very high. When coming to semiconductors, the band gap between valency band and conduction band is less, and in conductors, it is very less when compared to the semiconductors and insulators. Influence of temperature and doping. Temperature affects the occupation of energy bands in a material, leading to changes in conductivity. Doping introduces impurities into a material, alerting the energy band structure and conductivity. By controlling temperature and doping, one can manipulate the energy band structure to design materials with specific electronic properties. Applications of energy bands. Understanding the origin of energy bands is essential for developing electronic devices like transistors, diodes, and solar cells. Energy band engineering allows for the design of materials with tailored electrical and optical properties for various applications. Ongoing research focuses on optimizing energy band structures to enhance the efficiency and performance of electronic devices. Thank you. This is presented by Ashprita from Computer Science and Engineering Department. Thank you, ma'am.